right, so here we are. We got 48 stars. I'm going to see about 49. We'll see. Maybe 50 comes for free, like free. Maybe it just goes right from 48 to 50. Who knows? I don't know. All right, we'll talk about it in a minute if I get it. So here's my code. I got my little Doug the Pug here. He's happy. Oh boy, okay. GWH, comma, JCT, comma. This is exciting. RCB, comma, WBW, comma, WGB, comma, Z09, Z021, and Z39. And the answer is holy poo-poo-doo-doo-doops. Well, there you go. So let's talk about how we got there. Hello everyone, I am Bradley Sward and this is my day 24, part 2 solution to the 2024 Advent of Code. The problem is called cross wires. I'm solving it as always in Python. So again, real quick, for part 1, we're basically simulating, we don't know it yet per part 1, but we're simulating addition. We basically have a bunch of inputs coming from a bunch of places. Here's my x's and here's my y's. And at the end of the day, when you put this all together, the z's will be the solution to what is this number plus this number in binary. And then we can convert that to decimal or whatever it is that we see fit. So for part 1, let me pull that up in here. You run your code through this and you get the answer that you're expecting. And again, you can watch the part 1 video if that's more interesting to you, or if you need to kind of come back to talk about that. We have a bunch of rules and a bunch of variables. We run the variables through the rules and reduce the rules and turn the rules into variables as we see fit. And then we go and we look at all the z values and we print out the value and we get this large number 572 whatever, blah 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 blah, which matches up with the solution that I'm expecting to see down below. And there it is. You can see up here and my number matches. Of course the font doesn't match. So that's how part 1 works. So for part 2, we do learn about the fact that we're trying to simulate addition. And you're like, this sounds crazy. And it turns out I'm trying to simulate the addition of two 44-bit numbers. And so when it comes to everything there's 220 outputs to 220 different operations that need to go down to make one addition between these two 44-bit numbers work. And so if this is something that's interesting to you, where is it here? There it is. Here is, I use this every term with my students. We sit through the 18-minute talk, and it starts from basically just showing you how physically an AND gate works when it comes to like the physicalness of staring at, oh, come on, there we go. Nope, there it is. This is a NOT gate, but then where is the...
Oh, it's open.
Oops, where is the... Oh, there it is. There's an AND gate, and then an OR gate, and then it just makes it more and more complicated. We talk about all sorts of different stuff, and at the end of the day, we end up with these 4-bit adders, basically just a chip that we can use in lieu of for just having 4 bits added to 4 bits. Basically, I need 11 of these guys put together, and you get... I mean, I'm just presuming that the hardware and the software for this is pretty much a solved problem by now, such that whatever this would work out to, it would work out to the 220 wires. So just to say, this is a very cool video. If you've never seen something like that, how you go from nothing, and it's again it starts from knowing absolutely nothing to being able to add two 4-bit numbers together in less than 18 minutes, and negative numbers included, which makes it pretty cool. So anyway, so that's my talk about that. With that understanding, then the first couple parts of this is like a detective novel when it comes to trying to figure out what's going on with this problem. So like for my part 2, I have 5 different files here. And now that I've solved the problem and I've worked through it, now I know how I would write code to solve it for the general case. This, of course, I figured out how to do it because I went from how the heck do I do this, or what are even the problems. The assumptions, I can't make assumptions because part 21 kicked me in the because of the presumptions that I had made about the problem, because even in the problem they didn't indicate that things might go wrong in certain cases, and they definitely did, and it set me back by quite a long time, even just trying to understand, it wasn't my code that was wrong per se, it was just the presumptions that I had about the problems. So anyway, so for this part 1 here, or my part A here, I have this code, and you can see like this, as I was going, we will be able to prove that these are actually the wires by the end here. And so this goes through and goes, well, if I add the two numbers I was given from the inputs I was given, what should be the output? and the expected output was this. And when I run it through that number through the wiring I currently have, this is the actual value I get. And so it's wrong at these different places, Z09, Z10, Z13, Z21, 22, 23, whatever. And this just shows how many different variables and outputs are needed to get to that certain location. And so for the first thing I noticed was the number generally gets larger over time, and it generally gets larger 4 at a time. If you want to think, if it's just a sequence of 37, like 11 would have been 43, then 45, I'm sorry, 41, I can add 41, then 45, then 49. It seems like every jump up from one number to the next would require 4 wires. And it turns out that's absolutely true, and then that's the key that kind of solves everything here. So my thought was, as I was pushing forward, I'm like, well, there's a problem here at Z09, there's a problem at Z13, there's a problem at Z21, and there's a problem at Z39. And Z39, absolutely, that's one of the wires. Like right off the bat, I was like, oh cool, I solved 1/8 of the problem, because Z39 has to be an issue because there's nothing associated with it when it gives me a bad result. And then just going into the data, just looking for Z39, you can see that it is. Because X39 and Z39 gives me Z30. Well, no, there's more to that. That might work for Z0 and X0 and Y0. If we do a search for X00, you can see that. Oh, not there. Oh, I guess maybe so. Oh, I'm sorry, XOR. Here, let me find the next one. I'm looking for the XOR version of that. There we go. So this is correct. So because for the first one here, if I XOR X00 and Y00, I get the result, the Z00 I'm looking for. So this is actually correct. But everything else is much more complicated. And as we talked about, it seems like there's a four wire difference between X000 and Z01 and so forth. And to prove that, I wrote this code. And I went through, because again, I had presumptions, but presumptions could take days away from you when it comes to trying to find out a solution to the problem. So for this part 2, this tells me, and they're saying like, okay, what is this? All these OKs telling me? Well, all of these OKs from this part of the problem is telling me that each subsequent part of the problem is a larger set of the full set. So like if I was saying I started from basically just one bit, well that works just fine. And then so I'm like, well, okay, those wires will not be, those wires work. So then when I move on to the next one, I go, well, those wires do, and then so forth and so on. And so this is telling, when I do find a problem, that's basically saying that the problem has to be within those 4 or 5 wires, and we'll show that here in a minute too. So that's to say here, when I'm going through all of this, this is just to say that each step along the way, every wire that I find that's going to be a mistake is part of that subset, and then as long as I solve that subset, well, then I can move on and then find the bigger problems, and it all kind of comes together. So now that I know this information for part C now, I'm like, well, let's start solving for one of the problems. So this code here starts going through, and you'll see here, attempting bit count 1, 2, 3, and then I learned later on that, of course, and since we have subsets of problems and so forth and so on, that you don't have to test every single number against every single number, because that's what this is doing. This is testing every 1-bit number against every 1-bit number, basically x of 0 versus y of 0, x of 0 versus y of 1, and so there's 4, there's 16, 64, basically whatever the bit count is, you're doing 2 to the 2n power of addition tests to verify that every addition works. And I'm like, well, yes, this is why it's going to start taking forever and a day, is because, at least my code is exhaustively searching and testing every value against every other value to see that it's working out correctly. And so it takes 4 hours or something like that when I was running this overnight, the first night I was trying this, because I was just enjoying solving the problem here, just trying to learn from all of this. So this code here, all these passes for breakpoints and whatever. And basically what happens here is when I run this, let me rerun this for range of 9. Oops, that was not intentional. Starting from the 9, and you'll see that everything here works just fine, or at least it does work fine. It just takes a long time to prove it, exhaustively prove it. But when I start at 10, then it immediately crashes. Or no, it should crash. doesn't crash right away, but it does crash at a certain point. It will print failure at some point. I wonder when. There it is. There's my failures. And so basically, this code has proven that everything up for the 9 bits works perfectly. So then now for 10 and at least for 10, I have to watch out what's going on. And that fits with my theory here from the first part, because Z09 is the 10th bit. So then there is an issue here that we need to fix. And my bet was, and it did turn out to be true, was that if I fix that, I'll fix at least these 2 problems together, and then I need to move on to the next. So we'll find out that here in a second. So now that we know that the problem is in bit 10, and we know about the subset problem, and we know that everything up until that point is working, well, now if I find this wire map set here for 9 and 10, I can see that these are the wires that, or these are the outputs that are needed to solve the 9-bit problem, and these are the wires needed for the 10-bit problem. And there is a difference of five wires, this wire, this wire, this wire, this wire, and that one. You can get the names from down below here. And we don't care, I mean, there are 2 more each, but we don't care about the X's and Y's. They're not outputs, those are the initial inputs. So each time through, we're going to find that there's 5 wires where this, and basically we need to figure out which of the 2 are the ones that are swapped. And so if we come back to part D here now and we run this, I wrote this code now, this to fix things up, and it's not the most efficient. You can see I'm just working through it here to basically try each of those test cases and say that, okay, so there's going to be 10 test cases down here. I took those, the 5 different ones, and I'm running 10 tests, 4 of these, then 3 of these, then 2 of these, then 1 to make 10. And you can see that I ended up with 2 possibilities. It could be DSK and GWH, or it could be here possible for GWH and Z09. So so I've reduced down to basically it's one of these 2 cases. GWH is definitely one of them. It's just a matter of finding the other. And if I run this code and I change this up, instead of running it for these cases where you just try, where did it go here? My loops here, we're basically just trying all the powers of 2 minus 1, or one value minus that. So 1 and 3 and 7 and 15. Basically setting all the wires to 1, just as much chaos. 1 everywhere is going to be, like zeros everywhere doesn't get you much of a solution. So this will try a bunch of different sets here, and in this case, when I find out that the math doesn't work out, I hit a failure, and it tells me what values made it a failure. But for the limited testing I did, it turned out that these aren't the case. So if I followed this, and it'll take a lot longer, but if I replace this with this and reduce and make this a more exhaustive search, you find pretty quickly that GWH and Z09, at least in my data set, those are the solutions to part 1. And you can see that here, basically if I kind of reduce this and say, okay, let me swap that out and just make that the case, because if I swap it and then swap it right back, it's the same as not swapping at all, right? So let's see, so here, this can go and it will, so trying, and you're saying it's possible. It's going to say it's possible for everything because I'm only swapping the 1 here. But anyway, coming back here to the part, which part am I on here? Coming back to part 1, or part A of this, if I put this back in now and I say, okay, now let's swap those wires and run the initial tests again, you will see that now everything starts from Z13 and on. So I have solved the first problem, the first part of the problem. And from here, it's basically just solving this exhaustively, because now, then going through part D here and go, well, let's look at when Z is 14, because if this is the case and I'm swapping things out, and I'm not going to be swapping anything differently here, but just to say, but if I come back here and I don't worry about what I'm swapping and just say, well, as soon as I get to 14, the thing should crash almost immediately. And I don't remember if it does anymore since it's been a day or so since I've done this. So let's see. Failure, 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 failure. The failure is the important part here. It's not that what I'm trying doesn't matter. It's going to be the same, whatever. But that proves that bit 14 is the difference. So coming back to here, and now it's just a matter of coming here and just going, well, what are the differences between 13 and 14? It's this one, this one, this one, this one, and then Z13, and then doing it again to get the second part of the solution. And then it ends up being WGB and WBW in my case. And then I run this. this code again, and now you'll see Z13 goes away, and now I'm left with Z21, Z22, and Z23, and then, you know, so basically, and this will solve this problem, because when I solve this, it solves for Z21, Z22, and Z23. So there you go, and then you're reduced with that, and then when I do the same process one last time and I find out that this is the case, then it turns out that nothing prints out more, so I've solved the problem, and then that basically is everything there. So now I know, again, like through all of this and a couple days worth of just hemming and hawing, thinking things out of how I would solve this, and being thankful that they didn't make the problem more hard than it could have been. They could have made this brutally hard when it comes to what gets swapped and who knows what's and all the things, but they didn't, which was very nice. But just to say then, from there, well, now I know my 8 wires, and then when you saw at the beginning of the video, I popped it in, and everything worked fine. But anyway, coming back, I totally see how to make this automated now, so that you give me the inputs and the outputs. And so just to say, in some of these cases, the values that I tried, like the give you, I think for the fourth part, for the fourth set of wires, that it gave me it had two correct answers. It could have been one or the other. It could have been A and B versus A and C. It's like, but I couldn't tell which one was which because they only gave you one piece of data. They only gave you one number to add, but the problem said that it could be any, like basically, of course, any addition, any X, any Y needs to add correctly. So ultimately, if you do this right, you are creating, you're basically simulating an addition, on your ALU part of your CPU. So, but in that case, then I had to go back a little bit more and do a little extra work to figure out, that one of the two cases wasn't the actual answer, even though for the problem set given, both of them worked accurately. But then once I popped it in for just whatever, just random data, everything worked fine. So that is my solution to this problem. This was a fun one. This one was a little more, this one definitely didn't take as long as day 21, but it was still very challenging up there there was a lot that you needed to know ahead of time to get going on this to solve the problem. But it was a lot of fun. So for me, at this point, you'll see my video here. Everything's done. Advent of Code 2024 is complete, at least for me. What am I supposed to do with myself? I got 10.5 months until the next one, right? So anyway, so I hope these videos helped for anyone watching. And if not, at least I chronicled my work through it over the last month and a half here. Had a lot of fun, learned a lot, had a lot of challenge along the way. So thanks everybody for watching. I'll see you in future videos.